Today we're going to look at rate, time, and distance problems. And this is what we call the DIRT formula because it's D equals RT, so it's just easier to remember DIRT because, DIRT. Okay, so there's several different types of um, motion that we're going to talk about using rate, time, and distance. And each type is solved a different way. So let's look at this definition here. So it says an object is in uniform motion when it moves without changing its speed or rate. There are three types of uniform motion problems. Each can be solved with a chart, a sketch, and the distance formula. Now, here's the thing about uniform motion. In the real world, almost nothing moves in uniform motion. If I'm driving, my speed is changing constantly. I might be going 40, then 42, then 41, then 43, as the terrain changes. So I'm not ever going to be driving where I'm driving exactly, 45 miles per hour for the entire trip. Okay, unless I put on cruise control, but even then, the entire trip is not going to be uniform motion. So this is really something that we use in theory. When we're trying to find something theoretical, we might say, well, if the average speed is such and such, then we can treat it as uniform motion. Okay, so just know that things don't ever really travel at the exact same speed for long periods of time. Okay, so uniform motion is when it moves without changing its speed. And another term for speed is rate. So we use the rate. And there are three types, and we're going to use charts, sketches, and distance formula. Okay, so the first one is motion in opposite directions. Okay, and it's super, super critical that you make drawings or sketches of these to help you understand what it is you need to do. Okay, because they say a picture is worth 1,000 words. Okay, a picture is worth like a billion. Okay, so it is going to make it so much easier if you can just draw a little sketch. You don't have to be a good artist because, like, I'm not an artist, but all you have to do is make a sketch. Okay, so we have bicyclists Brent and Jane, and they start at noon. Okay, so they've given us a time period there from point 60 kilometers apart. So I'm going to start here, and I'm going to say these 2 points are 60 kilometers. Okay, and I'm going to have Brent here, and I'm going to have Jane here. Okay, and they rode toward each other. So Brent's going in this direction and Jane's going in that direction, which means they're going in opposite directions. Okay, so this is motion in opposite directions. Okay, uh, and rode toward each other, meeting at 1:30. Okay, so if they started at noon and they ended at 1:30, their total time was 1.5 hours. And I know I'm going to use hours because here they give me a speed with kilometers per hour. Okay, so it's in hours. So Brent's time was 1.5 hours. Jane's time was 1.5 hours because they both rode for the same amount of time. Okay, so far so good. Brent's speed was 4 kilometers per hour greater than Jane's speed. Okay, so let's look back at our chart here. They're telling us that Jane's speed was R. So Brent was 4 kilometers per hour greater. So Brent's would be 4 plus R, or R plus 4. So we have Brent's rate in terms of R, in terms of Jane's rate. Okay, so far we've still got just one variable, which is all we want. Okay, we need to find their speed. So we're looking for R, and once we find R, we can do R plus 4. So distance is rate times time. So I'm going to multiply these together to get each person's distance, because if you think about it, the total distance was 60, but neither one of them went 60. Okay, so Brent was going a little bit faster, so he probably went more than half, and Jane was going a little bit slower, so she probably went less than half. Okay, but we know that the total distance, if we add their two distances together, is going to give us 60. So we're going to find Brent's distance, which is R plus 4 times 1.5. So I'd have 1.5 times R plus 4 times 1.5 is 6. So that is Brent's distance, and I'm going to write it right here, 1.5 R plus 6. Jane's distance is R times 1.5, so it's just 1.5 R, 1.5 R. So if I look at this sketch, I can see that Brent's distance plus Jane's distance is going to be equal to 60. So I can write my equation, 1.5 R plus 6 plus 1.5r is equal to 60. And now I can solve this. So if I have 1.5r plus 1.5r, that's going to give me 3r plus 6 equals 60. I can subtract 6 from both sides. 3. And notice that I simplified the side before I started doing things to both sides. So 3r is equal to 54, and 54 divided by 3 is 18. So that tells me then that Jane was going 18, because her speed was r, 18 kilometers per hour, and Brent, who was going 4 kilometers per hour faster, must have been going 22 kilometers per hour. So make sure that you've actually answered the question. If you just solve for r and you're done, you're not really done. Okay, you need to tell me this was Jane's speed and this was Brent's speed. Okay, but having that picture, which was super easy to draw, enabled me to see what my equation was going to be. Okay, so that's motion in opposite directions. All right, motion in the same direction. Okay. So here again, we're going to draw a sketch. So a helicopter leaves Central Airport and flies north at 180 miles per hour. And I'm going to read this whole thing before I start drawing anything. 20 minutes later, a plane leaves the airport and follows the helicopter at 330 miles per hour. How long does it take the plane to overtake the helicopter? So they're both leaving from the same place. So here's the same place. So here's my helicopter. And I'm going to draw a little helicopter. You don't have to draw a helicopter. And that actually looks nothing like a helicopter, but we can pretend, okay? And then I'm going to draw my plane, and the plane is going to be catching up to, yeah, that's even better. The plane is going to be catching up to the helicopter. So that tells me by looking at this picture that their distances are going to be equal, okay? Because when the plane catches the helicopter, they're both leaving from the same place, they're meeting at the same place, so their distances will be the same. Okay, so let's start filling in our chart now. So the helicopter is going at 180 miles per hour, and the plane goes 330 miles per hour. The plane is T, and we knew that the plane took off 20 minutes after the helicopter did. Okay, so the helicopter would be T minus 20. Now here's where you have to be careful. 20 is 20 minutes, but we're looking for hours. So 20 minutes is 1/3 of an hour. So we would say T minus 1/3. Okay, because 20 minutes equals 1/3 of an hour. 20 over 60 is 1/3. All right, and then we know rate times time is equal to the distance. So this is going to be 180 t. Make sure you do not write your units inside your equation. That just messes you up. So 180 t, and 180 times 1/3 is the same as 180 divided by 3, which is going to be 60. And here this will be 330 t. Now we already looked at our sketch and said that the distances are going to be equal. So I can write my equation, 180 t minus 60 is going to be equal to 330 t. So with these uniform motion problems, your equation is based on the relationship of the distances. For this first problem, we said that the two distances had to add up to 60, so that's how we got our equation. For this one, we know that the two distances have to be the same, so that's how we got our equation. Okay, so usually your information is going to be the rate and time information. You multiply those to get the distance, and then you say, okay, well, what is the relationship between the distances? Here they're equal. The last one, they were added up to 60. So now I can solve for t, and I'm going to get t on this side over here. So I'll subtract 180t from both sides, and that's going to leave me with negative 60 equals, and then 330 minus, what am I doing wrong? Yeah, 330 minus 180 is 150 t, and so t is equal to, and for some reason my negative doesn't seem right. No, because the helicopter left early, so this should be a plus 60. And I am instantly found my mistake because I'm looking at this going, well, the t can't be negative. Okay, so the helicopter left 20 minutes earlier, so its time was actually 20 minutes more than the others. Okay, so we fix that. All right, and then I have 60 divided by 150, and you're going, oh no, it's a decimal. No, it's a fraction. So that would be 60 over 150 is equal to 2/5. Okay. How long does it take the plane? So all we're looking for is t. We just want to know t. Well, 2/5, what does that mean? It's 2/5 of an hour. So 2/5 times 60 minutes, that would be 24. So it was t is equal to 24 minutes. Okay. So this is where, again, it gets a little bit tricky. Because our rates were in hours, we had to do our time in hours. However, they gave us minutes, so we had to convert the minutes to hours, okay? And then when we get our answer is in hours, and we have to convert it back to minutes, okay? So make sure you're cognizant of that, that you're aware of that, and you're not giving me, weird things. If you did this as t plus 20, you're going to get the wrong answer, okay? So just keep that in mind. And usually it's only time that is kind of screwy like that. All right, so the third thing we're going to look at then is round trip. Okay, so let's read this one. A ski lift carried Maria up a slope at the rate of 6 kilometers per hour, and she skied back down parallel to the lift at 34 kilometers per hour. The round trip took 30 minutes. How far did she ski and for how long? So let's draw our picture. So here's the bottom of the hill, and here's the top of the hill. And there's our hill. Okay, so we've got the ski lift goes up, and then when they ski, they go back down. So notice that the round trip, they're going the same distance each time, except once they're going up and once they're going back. Okay, so the rate for going up was 6 kilometers per hour, and the rate for going down was 34 kilometers per hour. Okay, the time to go down, they're telling us, is t, and we need to find out t. So the time then for going up, if the whole thing took 30 minutes, so 30 minutes is equal to 1/2 hour. So if the whole thing took half of an hour and it took t minutes or t hours to go down, it must have gone 1/2 minus t to go up. Okay, if that makes sense. So 1/2 is the total. A half of an hour is the total. So half of an hour minus the time it took to go down is equal to the time it took to go up. So we're just going to multiply. So 6 times 1/2 is 3, and 6 times t is just 6t. So I have 3 minus 6t, and then this will be 34t. Okay, and now again, we need to look at this. What's the relationship between the distance going up and the distance going down? Well, if we look at our picture, the distance going up and the distance going down are the same. So our equation then is going to be 3 minus 6t equals 34t. Now let me make sure I haven't made any really stupid mistakes here. So we said that 30 minutes was half an hour. So half minus t gives us the time going up. T is the time going down. The rate going up is 6 kilometers. The rate going down is 34. So 6 times 1/2 is 3. 6 times t is 6t. And 34 times t. Okay, and we know that the distances are the same. Just wanted to make sure I'm not doing anything really stupid. So I can add 6t to both sides, and I get 3 is equal to 40t. So t is equal to 3 over 40. Remember, this is hours. So 3 over 40, how many minutes would that be? We're assuming it's minutes because the whole thing only took 30. So 3 over 40 times 60 minutes, okay, because this is 3/40ths of an hour, and an hour is 60 minutes. So I can simplify this. If I divide by 20, that's 2, and that's 3. So I get 9 over 2, which is 4.5. So it takes 4.5 minutes. That's craziness. 4.5 minutes to go down the hill, which means that it takes 25.5 minutes to go up the hill. Doesn't seem worth it to me. 25.5 minutes to go uphill, and then only 4.5 to go downhill. Of course, 4.5 minutes is a lot of damage you can do to your body in 4.5 minutes. Okay, so to try this then, read the problem. First decide if is it uniform motion in the same direction, in opposite directions, or round trip. Okay, and it helps to read through the whole problem maybe once or twice before you start doing stuff. Draw your sketch, fill in your information, okay, and then write your equation and solve it. And I'll go ahead and give you a hint on this one. I'll tell you what you should do for your variable. So we know Carla's rate. We know Dean's rate, so we're not looking for rates. We're looking to see how long will it take if Dean bikes at blah, 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 how long will it take to catch up with Carla? So we're looking for Dean's time. So I'm going to say make that your T. Okay, so when you find T, you found Dean's time. Make sure you pay attention to whether, because this says 15 minutes, so you're going to have to convert things from hours to minutes and back again. So be real careful with that.